Welcome back, everyone. We are ready to start our next presentation. As you can see, our speaker is already on stage, so quick introduction and we'll be right off. So our next speaker is Zbigniew Skowron. Zbigniew is head of engineering at Precision Life, specializing in C++ development along with Python and TypeScript. His expertise spans from disassembling machine code to developing websites. As a game programming enthusiast, he participates in game jams whenever he can. Zbigniew feels most successful when deleting code, ensuring that only the essential and minimal remain. His fun fact is connected to those game jams he attends, as he completely disregards the theme of the competition, finding more fun in creating his own projects in his very own way. Before Zbigniew starts, please remember to rate our speeches, all the lectures in the conference app. And without further ado, please welcome to the stage Zbigniew Skowron talking about inside CPUs and GPUs.
Okay, so hello everyone. Thank you for coming. And let's talk about what's inside CPUs and GPUs. This is a relatively modern CPU, server CPU from AMD. And as you see, it is quite big. In the middle, you see an I/O die, which contains memory and I/O interfaces. And it's surrounded by a lot of CPU cores, 192 in this case. So this is a beast. And as you see, it is quite small. It's like this big. To give a bit of perspective, light, during one cycle of the CPU, light travels just the size of the CPU itself. So one cycle is like a very tiny amount of time. Electricity within the CPU travels even slower. It's like a centimeter or thereabouts. And within this one cycle, each of those 192 cores can execute multiple instructions. So that's pretty mind-blowing. So this is a close-up on an older CPU. We have 8 cores here in 2 groups of 4. And we can clearly see where the actual cores are and L2 and L3 caches in the middle. So we already see that even on the CPU die, the most of the space is just caches. Now, when we look at the actual core itself, we see it has a lot of various functional units. So let's see what's there. So we we have a lot of caches. Like half of it, or thereabouts, is still caches. So you have data cache and instruction cache and translation look-aside buffer, which is, again, cache. And in addition to that, even more caches are in the GPU, and even more memory is in GPU, in a CPU. Here we have units responsible for memory and some other things, but memory related. So here we have a big chunk of the CPU, which is just devoted for instruction decoding. Instructions on x86 processors are particularly complex. They are in multiple different sizes, and they have multiple different encodings. And decoding them takes a bunch of time, and it's a lot of work. Here are the bits that are the smartest parts, I would say, in the CPU. So we have branch prediction and reorder buffer, which helps with both out-of-order execution and speculative execution. And here we see the actual arithmetic units, so integer units and floating point vector units. And as you see, they are pretty small, right? So most of the CPU is, first of all, memory, and the rest is just units that simply make sure that those relatively small compute units have some work to do. So the CPU starts by fetching and decoding instructions. So it fetches instructions from memory, and then it then splits this data into instructions, and then starts decoding them. And splitting into instructions is not simple because it's x86, and decoding, like I said, also very complex. And then the CPU will convert those complex instructions into micro operations, and sometimes fuse some of them together to form more complex ones, and then it will start executing. So the first stage of the pipeline in the CPU is instruction fetch, and then instruction proceeds to decoding. But while it happens, the CPU already fetches another instruction. And when our instruction proceeds to execution, the next instruction is decoding, and another one is already fetching. So we have this pipeline that gives us instruction-level parallelism, where a CPU has multiple instructions in flight at the same time. A real pipeline in a CPU is, of course, more complex. This is a pipeline from CPU used for PlayStation 4 and Xbox One. And as you see, the fetch stages and the code stages take a big part of the pipeline. So the pipeline is quite long. It can have a lot of instructions in flight, and not all instructions follow the same path through a pipeline. Some are more complex, some are simpler, and we see that there are some overlaps. Okay, but the pipeline is only efficient when it's filled with instructions that are executing. But this is not always the case. Sometimes when instructions don't come in time from memory, the CPU doesn't have anything to put into the pipeline. So we have an empty space there. Or when we have an instruction followed by another instruction that uses result computed by the previous instruction, well, this following instruction has to wait some time until the result is ready, and it can use it for its own computation. So we have those empty spaces in the pipeline that are just losing performance. So what the CPU can do to make sure that the pipeline is filled. So for example, it can use branch prediction to predict which code will be executed next, and therefore fetch instructions from memory in time. Another technique is instruction reordering. When you have dependencies between instructions, CPU can reorder instructions into to try and fill spaces in the pipeline. And there's also simultaneous multi-threading or hyper-threading, as called by Intel. And it's a technique where two threads are physically scheduled on the same core at the same time, and CPU is free to fill the empty spaces in the pipeline with instructions from another thread. So CPU is divided into two pieces. There's a front end that fetches and decodes the instructions, and it prepares the queue of micro operations that then is used by the backend. And the backend contains all the compute units and does the actual work. And a funny thing is that in case where the front end already has filled the whole queue of micro operations, in some processors it can turn off to save power. And the backend is actually quite capable. So in the Zen 4 processors, for example, you have 8 integer units and 6 floating point units in the backend. So during every cycle, every single core can execute at least 10 or more instructions. So this is really quite amazing. And because of that, it's actually typically the case that it's not the backend that is the bottleneck, but the front end. The backend is waiting for front end to generate enough instructions for it to have something to do. Okay, so let's talk a little bit about branch prediction, because this is actually way more interesting than people typically think, because the CPU starts with just this red box on the slide. So CPU starts knowing only the address in memory where the instructions will be. The CPU doesn't know yet what this memory contains. It haven't seen any bytes. But still, based on this address only, it will guess where the instructions are within this block of memory. And it will guess if there are any jump instructions. And it will guess which of those will be conditional. And it will guess again if this condition will be true or false. So whether the jump will be taken or not taken. And after all that, it will guess where the jump will go, because it might go to many different places. And CPU will make a best guess and will start fetching the instructions. So that's pretty impressive that a lot of that happens without CPU ever seeing a single byte of an instruction. But then further down the pipeline, as the CPU actually gets to see the instructions and starts to decode them, it can run a more sophisticated predictor and make a better guess that will maybe override the previous one, in which case CPU will roll back and try again. And there are multiple different branch predictors. So you have branch predictors for indirect calls, like virtual functions, for example, which can have multiple valid targets. In one iteration of the loop, the virtual function will be called from one class, and on the second one from another one. So you have predictors that can actually store multiple targets for every single branch. And you have specialized predictors, like predictors for where the return from a function will go to. You have predictors for loops, because loops are very regular. So custom predictors for that works best. And you have predictors that are local predictors that like record history of this one single branch and then try to predict the next one based on that. But you can have global predictors that record history of other branches as well and make predictions based on this richer history. And you can have predictors that are hybrid predictors, where they look at the performance of other predictors and try to estimate which predictors works best for any given branch in your code. So yeah, the bottom line is that branch predictors are never wrong, basically. So never wrong is like a maybe overstatement, but they are between 2 to 7 incorrect predictions per 1,000 instructions. So this is pretty good, and actually it's on the lower side, right? And the modern CPUs have even predictors that contain small neural networks inside them. So like AI technology, basically. Okay, but once the CPU guesses where the control flow will go, it won't just sit down idling its thumbs. It will start executing those instructions. But of course, those might be the wrong instructions. This might have been a wrong guess. And in this case, the CPU will just roll back. So what does it mean to roll back the execution? Well, first of all, the CPU will flush the pipeline from all the instructions that are currently executing. And like we've seen, there may be a bunch of them. And secondly, it will remove data about all the instructions that have already completed but are waiting to be committed. Because a CPU will never commit any result unless it is 100% sure that it was executing the correct code. So the CPU rolls back everything that it guarantees will be correct. But it doesn't roll back other things that it doesn't make any guarantees about. So for example, it doesn't roll back the cache, because cache is just an optimization. And basically, you cannot depend on something being in cache. CPU is free to do whatever it wants there. So yeah, we cannot depend on those things that CPU does not guarantee, but hackers can, and they do. So basically, hackers are writing buggy software for profit, which we all do, to be honest, but they are the bad guys. How does that work? So everyone heard about Meltdown and Spectre, right? So the most famous vulnerabilities of recent years. So just very quickly to remind everyone what that was all about. So in case of Spectre, we had this code where code accesses our array, our memory, but using some kind of a secret that we shouldn't have access to. Something that we are not allowed to read. But we have a code that accesses that, like uses that to index our array. And we trick the CPU to predict that this code will be run. It shouldn't be run, but we trick the predictor to run this code speculatively. And what happens? Well, the CPU can read this memory and fetches the appropriate piece of memory into cache. But then it figures out that it was a mistake. It should have never entered this piece of code. So it rolls everything back. But it doesn't roll back the cache. So then we access every single piece of our array, and we measure how much time it takes. And we notice that one of the accesses for one specific index was faster than the other ones. So it must have been in cache. And the only way it could have been in cache is if it was loaded using this secret index. So this way, the secret was leaked to us via the cache. But, you know, Meltdown and Spectre happened a long time ago. They are ancient history, 2008. So surely this is a solved problem by now, right? But actually there are multiple reasons why a CPU might roll back some execution. And in case of Spectre, it was mispredictions. So branch prediction made a mistake, and we rolled it back. And in case of Meltdown, it was access errors. But there are other things, like the normal floating point values that cause a CPU to just scratch some computation, or self-modifying code that, you know, CPU started executing code as fast as it could, but then it noticed that in the meantime, someone modified it. So it needs to scratch that and start over. And there are memory order issues where CPU will just assume that the data it has is good, because that's the fastest way. But then, after executing instructions, it will actually check if this data was the newest version. And it turns out that maybe sometimes it wasn't, so it has to roll back. And also, when CPU is accessing cache, it sometimes can get data from cache and just start using it without looking in details if this data is even correct. But then it will check if it was correct data, not some garbage. And sometimes it was wrong, and it needs to roll that back as well. So security researchers are finding a lot of new vulnerabilities like that, like all the time. And we have you know, various funny names on the slide, and various nice logos that come with them. And it's happening like constantly. And there are various mitigations for those vulnerabilities, like fixes to CPU designs, microcode updates, unmapping of kernel memory from user space, so that it physically won't be there in case someone would like to leak it. Compilers can inject extra instructions when they detect some fragments of code that might be potentially exploitable by some of those attacks, and they will insert instructions that prevent speculative execution. Browsers, for example, move sensitive data to other processes to kind of hide it a little bit better. And you know, on cloud servers, you might want to actually get a physically separate server from other cloud tenants to make sure there are no side channels that someone from the outside can use to access your data. And those mitigations are very costly. You know, up to 50% of performance loss. And fundamentally, those vulnerabilities are not patchable. Like, as long as we have speculative execution, this will be here. Okay, but CPU does a lot of things. So, for example, it might turn out that it was fed invalid instructions. So, what does the CPU do then? Well, typically, it will just report an error, invalid opcode, and that's it. But sometimes those invalid instructions actually do something. You know, they might be some instructions that were buggy and therefore not actually published, but they are there and they are doing something. And earlier this year, researchers have found in some RISC-V processors some very interesting invalid instructions that were giving read-write access to arbitrary memory, all of the physical memory accessible to the CPU. So that's basically a game over, right? You can do anything with that. So that happens too. Okay, so how do we harness this this complexity? Well, in 2004, Herb Sutter had this published this article, "The Free Lunch is Over," where he was talking about the multi-core era and how it's here. But really, are we still here? Because like in Python, you don't really have multi-threading. I mean, well, there are some things, some people would claim it has, but not quite. JavaScript, same story. And in C++, it is way better, but it is by far not the solved problem. People are actively researching new async primitives, senders, receivers, channels, and other things that would help us actually harness even the multi-core. But that's not everything. 10 years later, Mike Acton introduced the masses to data-oriented design in his famous talk, where he proposed a paradigm for programming that is cache-friendly, SIMD vectorization-friendly, and parallelization-friendly. And the main idea is that when you have something specific that you want to operate on, you should never take one thing. You should always take a lot of those one things. So there are other ideas as well, like value-oriented programming, which is both a security thing and also a performance thing. And in the GPU world, you have SIMT, so single instruction, multiple threads. So basically, you have multiple threads that in the hardware are actually executed on the SIMD vector units under the hood. So let's talk about that. So this is the Blackwell GPU from NVIDIA. And this is what it has inside. So this is actually from an older architecture. But basically, a GPU has a lot of symmetrical multiprocessors. And it will have, like in your laptop, it will have 20 of them. In a server GPU, it would have over 100 of those things. And each of those will have 128 cores inside. So you have like, in a laptop GPU, you would have 2,000 cores. In a server GPU, you would have like 20,000 or thereabouts. And each of those multiprocessors has a lot of integer and floating point units. It has tensor core units. It has various other things. So why the CPU was a kind of a corporation that has a lot of bureaucracy and middle management and very few people down the bottom doing the actual job, the GPU is like a factory. It's like all about compute, right? Very little of this management. But in order to feed data into those compute units, it has to have a huge memory bandwidth because it needs to get the data from somewhere, right? So in fact, which is quite surprising for many people, GPUs are not only like compute-focused machines, they are also memory-focused machines. So if you have memory-intensive workloads, GPUs are also way better at those than CPUs are. So we have a symmetric multiprocessor, and what it has inside. Like I said, it has 128 cores in NVIDIA, and it can store up to 2,000 threads inside. What does it mean that it can have threads inside it? Well, it means that actual physical resources on this core, on this symmetric multiprocessor are assigned to this core. So like the registers are storing values for those 2,000 threads. So they are ready to execute. It's not like on a CPU world where you have like switching thread in, switching thread out. They are all active there in silicon. And this multiprocessor executes threads in blocks of 32 threads at once. So those block of 32 threads is called a warp. So how does that work? When the warp is executing, at some point it will need to access memory. And the memory is not there. It needs to wait for it to arrive, which takes a long time. So the GPU will just put this warp of 32 threads on the side, and it will take another one, and it will start executing it. And this thread will also stall on a memory fetch, and the GPU will also take this thread and put it aside, and take another one, and so forth. So while a CPU has 32 kilobytes of cache per core, a GPU has bytes of cache per thread, bytes. So virtually no cache at all on a GPU. So the CPU is hiding memory latency using cache. And the GPU is hiding memory latency by massively oversubscribing with work, and with work that is instantly ready to run. So the interesting thing is about warps that all those 32 threads execute in lockstep. They execute the exact same instruction at all times, right? So in the same chip, right? So what does it mean? That they can actually communicate within an instruction. So we have instructions that actually exchange data between threads in a warp because they are doing this thing at the same time in the same chip. Okay, but what about conditionals? You have ifs, and some of the threads would like to go to the if block. Some of those would like to go to the else block. What with that, right? So one option is to use predicated instructions, where each thread computes its flag, and then instructions in the if block are predicated. You know, they execute when the flag is true, and the instructions in else block execute when the flag is false. So still, all the 32 threads in a warp execute the same instructions, or are executing both the if and the else branches. It's only that some of those instructions are just turned off in some of those threads and not in the others. Okay, but this doesn't work great in all cases. For example, if you have a lot of nesting, you would have multiple flags, so it's kind of tricky. So another thing that the GPU can do is to mask threads. So basically split a warp into two, and it will first run part of the warp, executing the if branch, and then we'll switch to executing the second part of the warp, and executing the else branch, which is, of course, less effective, right? Because part of the GPU is not doing anything, it's just waiting. And the usage of the underlying vector units is like not full. So this is suboptimal. So if we go out of the if, like we would like to converge the whole warp again, so that all 32 threads will continue working together. And sometimes it is possible, but when there is some thread synchronization going on, the GPU cannot do that automatically without programmer's assistance, because there might be a lock within the if and unlock somewhere after the if. And if the GPU would just wait for every thread to exit the if, it would wait indefinitely. So this reconvergence might not be always possible. But there's another interesting thing, because at the same time 2,000 threads are physically in this one processor, they are not executing at the same time, but they have all the data there. So those multiprocessors have a little bit of internal memory that those threads can use to communicate between each other. And because this is within the chip, it is super fast. So those threads that are doing the same thing on the same processor are called blocks of threads. And you can leverage this locality to one single chip to gain huge performance. And similarly, multiple multiprocessors that are together form a cluster of multiprocessors, and because they are close, they can communicate very fast. They communicate faster than with some multiprocessor at the other end of the GPU. So again, this is all exposed in the programming model of the GPUs. You can actually use the fact that you have some threads executing together with you, that some threads are executing on the same processor, or that executing on a nearby processor. And all of that is exposed, and you can leverage that. And we don't really have anything like that on the CPU side. Okay, so everyone knows that memory access on CPU is best when it's sequential, right? Because we have data in cache, and we just read data that is in cache. But in case of GPUs, when you think about each thread accessing memory sequentially, its own table of memory sequentially, then we see that when all 32 threads in a warp are considered, they actually access very different parts of memory. So the GPU has to load, because loads from memory don't ask for a byte. They ask for like a huge chunk of memory at the same time to increase the throughput. So the GPU has to load a bunch of memory, then your threads read and use only a tiny fraction of it, and the rest goes to the trash bin. It's forgotten. And then you get another memory access, and the same thing happens. Because this memory was not cached. GPUs doesn't have enough cache to do that. So you basically throw out most of the data that was fetched from memory. So instead, what you do is that you consider all 32 threads at once. So you make sure that first thread is accessing the first element, second thread is accessing the second element, and so on. And this way, all 32 threads are accessing this one chunk of memory, and then you move all of those threads 32 indices to the side, and they again access another contiguous chunk of memory, and then they move to the side and access other chunk continuously. So this is now sequential, right? And warp level communication is also very useful in graphics. For example, when you have a game that renders a polygon on the screen, some polygon in the distance, you can have 2 pixels that are very close, like neighbors on the screen. But because the polygon is so far away, they actually map to very distant pixels in the texture. So this will produce those aliasing artifacts, those noisy textures that just look bad. So the answer is MIP mapping. So the GPU will store not only the full-sized version of the texture, but also smaller sizes, up to the 1x1 texture, just 1 pixel. And when rendering neighboring pixels on the screen, it will choose the texture where those pixels map to neighboring pixels in the texture. So this will achieve you two things. First of all, you have much better quality because those textures are filtered and you don't have those aliasing artifacts, so the pictures look nice. And also because they are close in memory, you get way faster accesses. So how does that work? Well, the GPU guarantees that whenever it renders a pixel on the screen, a block of 4 neighboring pixels is computed together. So you know for sure that if you are being rendered, your neighbors are rendered at the same time within the same warp. So if you compute your texture coordinates, you can just say, I know that all the other guys have computed that as well in the same instruction. So we just say, OK, I will give you mine coordinates, you will give me yours, and we'll compare them and compute the delta. And this way, we know how far from each other we are, and we can select the proper texture and fetch the data. So this is pretty cool. But GPUs have a bunch of other things as well. So for example, they have tensor cores that allow to compute matrix operations. And what is interesting about those is that they are not directly programmable. You have to use call a function provided by NVIDIA that does this magic thing. And also, it's not a thing that one thread can do. Only all 32 threads in a warp together, they can compute just one single result. So typically, each thread computes its own thing. But in this case, all 32 threads together use the tensor core to compute just one thing. Another thing that GPUs can have are ray tracing cores, but those are only in the GPUs that are actually used for graphics. And they can compute bounding volume queries. So basically, just you can ask in a game like what objects are near this place, or you can have ray tracing queries asking whether a given ray intersected given triangle, which is of course used for computing nice reflections and nice lighting and other effects like that. But this is kind of less fun because you cannot program those cores directly. You have to use an even higher level API like DirectX or Vulkan. So yeah, but it's there. It's quite interesting. And yeah, so the main takeouts are that the CPUs are fast because they guess a whole lot. They guess everything, and they assume everything, and they are almost never wrong. And GPUs are not only great for compute, but also for moving a lot of memory. And the GPUs expose their hardware internals in the programming API, and you can leverage that, which is very kind of alien experience when you start with it, but it is really quite cool. And while CPUs hide memory latency using caches, GPUs just oversubscribe with work to hide this latency. And yeah, while we have a lot of multiple or different programming paradigms to try and leverage this hardware, like all of them has some drawbacks, some pros and cons. So it's difficult to choose from. And yeah, the final note is that unfortunately, hardware vulnerabilities are here to stay, at least for the for the nearest future. So thank you very much for listening.
Thank you very much, Zbigniew, for this extremely interesting presentation. But I'm afraid, guys, we don't really have time for questions after this one. So thank you very much. Thank you, Zbigniew, again.